more died in 2020 than have died previously.
Live from Los Angeles.
What is happening now is
Saturday
about 60% more dying every week than died on 5-year average previous to COVID.
But if we're vaccinated.
And there seems to be vaccination that's doing most of it.
Okay.
Some of it's applicable to people not getting health care. But about 13% down to vaccination, it seems.
What if that's true?
Yeah.
Okay, people, can we move on, please? We have a talk to listen to.
Well, I don't know.
Your attention, please. Live from Los Angeles, we have the distinguished. It's Saturday night. I'm going to press the record button, and Divyamaan is on stage. All right, ready to go?
Yeah.
Go.
Awesome. Thank you so much again for, hi, question already?
Can you put on a microphone because we can't understand you with the mask on as well?
I'll take the mask off.
Okay, fine. Are you guys okay with that?
Yeah, we're fine.
Alright, fine. So, thank you everyone so much for hosting this talk. I was supposed to give this talk last year online, but unfortunately I could not do that because I was working at this as a volunteer at this arts organization in the middle of the woods, doing roofing work and shingles and things. So unfortunately I could not join online last year. So I'm very, very grateful that to be here in person. We just came from a Laws of Form conference, and this talk is very much connected to Laws of Form and Spencer Brown work. And in particular, I would like to show this picture, which is the mark of distinction, which is nested into itself. If you're not familiar with Laws of Form, it uses just a single mark of distinction. And of course, I'm more interested in this this nesting of the mark into itself. And I would just like to show a picture that it's really, this talk is really a meditation on circularity, on things talking about themselves, on recursive distinctioning, and there are many ways of talking about this. And really, you'll see that I'll keep trying to circle things back into themselves and see what structure or what it ends up telling us. So there was a diagram that that I found in Lou's notebooks, and also it's sort of a part of discussions that's connected to this nesting of the mark. But Laws of Form doesn't have a way of talking about this diagram, and I'm going to show it to you very quickly. It is this diagram right here. So what exactly is that? You have a nested distinction re-entering itself, but it's also sort of circularly re-entering itself in a certain way. And so when this picture, when this diagram sort of popped up, that sort of served as a source of inspiration for, okay, like, how do we use Laws of Form to talk about arrangements like this that you can draw on a flat piece of paper on a page. And so I'm going to talk about this paper, which is OO, and of course OO and OOO are three papers, and they're it's just a cheeky thing, but it works. So the way I start studying this diagram essentially is that really, if you look at this mark within mark within mark within mark, it's really coming from a paper that Spencer Brown has written called Design with the NOR, where the mark of distinction really is a NOR gate. It is a gate that, really what happens is you're kind of evaluating an arrangement as a circuit that involves the NOR gate. And so, so really it is, the NOR gate is the mark of distinction.
So NOR is neither or, is it? NOR?
Yes, yeah.
Or.
Yes.
Not or.
Yeah.
Not or.
And we don't need to fixate on the logic part of this. Really, it's the idea of like you're evaluating such expressions, that you're passing through a boundary, that you're going from the inside to the outside. So if you just make a mark of distinction here, you're moving from the inside of the mark and you're going to the outside of the mark. And that really is the main focus of this. It's less about the NOR aspect of it, but more about the fact that it is a mark of distinction, that you're passing through a boundary. So, really this is just one mark, but if you have successive marks that are nested into themselves, you have this collection of successive NOR gates, and really it looks like a solenoid in a certain sense. But where I'm trying to go with this is it's really there is a notion of, okay, you want to put this circuit into itself, and you have these successive NOR gates, which you can really think of it as a NOT gate, because something that goes in, if it's true, it flips to a false, and if a false goes in, it flips to a true. So if you have a circuit with just one gate, and if you have an input, 1 going in flips to a 0, and then the 0 going in flips to a 1, and then the 1 going in flips to a 0, and then the 0 flips to a 1. And Lou has drawn these diagrams ad nauseum actually in many of his essays. And so you can think of the re-entering mark just as a simple oscillator with one inverter, and it flips, and you get a square wave, and that's really the basis of laws of form. But here what happens is I start thinking about this as really a way of evaluating this mark within mark within mark within mark circularly as a torus, really. I mean, but it's a solenoid that it's bent into itself. And what I want to talk about here is really a relationship between electricity and magnetism that is really elementary in a certain sense. I guess we have encountered this in high school physics, right? Where you have Hans Christian Ørsted, who noticed the needle of the compass deflect away from the Earth's magnetic north when brought close to a current-carrying wire. So you have a wire that has current flowing through it, and really the discovery that it has a magnetic field that is produced in a current-carrying wire. But he is supposedly the first to see that these magnetic field lines are circular. So if we want to look at this picture for a minute or two, here we have a circular electric current which is going in this way, and really this we're going to talk about the right hand thumb grip rule that has come from Ampere, or I mean really it's natural now in orientations of curves and surfaces, that if this is if the curled up fingertips are the current, then the thumb is the magnetic field, that it gives you the direction of the magnetic field. And so this is the same thing. You have a current that is moving in this orientation, and then you have the magnetic fields pointing up here, right? And then really this is a switch in perspective, right? This is still your current, and you're getting a magnetic field. It's a little hard to see in this picture, but really it's like a funny circularity of like, okay, one is inducing the other thing and the other is being induced by the one thing. So really this is the heart of the whole thing, where you have the right hand rule, and this is what I decide to do, which is so if we have a current carrying, like if we have a circuit and we have a magnetic field that's pointing up, what if this were to re-enter itself? I don't know how to do that with my body, but but you can imagine that picture, like. And so what we're doing is we're really imagining a coiled, you have a solenoid that's being bent onto itself. But we know that this also, that there's a direction in which this torus, this coiling is happening, and so we can use the right-hand rule on this again, on this entire thing, and that whole system can again go around to make another larger torus. And this process will repeat indefinitely. And I of course, like I have made some pictures here in this essay where this is really a very condensed way of saying what I was saying here. Where, okay, you start with this, you use the right hand rule, then you get the first torus. Then this torus also has an orientation, and you use the right hand rule on that again. And then you make another, you keep jumping up orthonormally. And so you start making these diagrams that are really jumping up and up out of the page every time. Whenever you use the right hand rule, you're jumping out of the flat surface on which you've drawn the circular distinction. Because of the right hand rule will indicate where the magnetic field's going, and then you circulate that, which gives you the new distinction. Then you do the right hand rule on that, and then push that out, which gives you a new circular distinction. And then you use the right hand rule again, and then you know what I'm saying. So you keep doing that indefinitely. And of course, I keep doing it like horizontal, vertical, horizontal, vertical, horizontal. I mean, I draw it that way. But you needn't do that. You could like angle it a little bit and see more dimensions on a page. That's another way of drawing that. But yeah, you could draw it a little, skewed. So I will just show you the progression of these diagrams where I was saying here you have this the orientation of this torus, or you could say coiled toroidal solenoid, because that has a direction, and you use the right hand rule on this, and you can make an even larger what I guess I call it a monstrous torus. It's nothing really. I mean, it's just the beginning, because that can obviously go larger, and that becomes even more monstrous. So so really this presentation is the heart of this presentation is this idea of using the right hand rule and re-entering it, and that as a method, as an inductive method to create higher genus surfaces, essentially. I think that was sort of what I wanted to share really in last year and this year. And so I can share more things which I've opened up around here, and the tabs. So really I'm coming at it from a perspective of course laws of form is very strong here. And essentially I end up using this as a way to create a number system, a number system with orientation, if that makes any sense. And you can count ordinally. You can really start looking at transfinite ordinals in this. We have, and I'm going to show you the essay O, because now that we know what this, we have this background of the right hand rule re-entering itself. And this essay is really the first time I've made an essay that has no words in it. There are absolutely no words in this essay. It's entirely visual, entirely diagrammatic. And it started off with a few words peppered into the essay, but at some point I just decided that I don't want to use any words anymore. I just want to use diagrams and see what happens, because I think diagrammatics are very important and powerful, and of course sound to me is very, very powerful as well. But in this case, it was really a reasoning of I just wanted to I wanted the reader to be released from this pressure of words, and just using pictures and simple but strong diagrams to sort of indicate what is going on. So I'm just gonna go through this essay really quickly, where really there's this idea of starting to put things in a circle, and you can imagine it like, okay, I have a number line that's a line, but what if I were to bend the number line onto itself, which is really a projective number line, right? Many of us talk about that. So really I start counting these turns of this toroidal solenoid, or the number of rings on on this base, and I start counting using the circle as a tally mark on the circle. So really that's 1, 2, 3. You can start counting on this circle, and everything is really circular here. So I have a way of like really, if you, I mean, I don't want to add any words to it really, but there's like, I used to have 2, 3, 5, so 2 and 3 make 5. I mean, it's really coming down to a very basic, simple thing, and then you have like 3 2s, 2 3s, 1 6, and then you have the equals is like a double circle. And here's another notation that I start using, which will be explained later. But again, like this is the power of just diagrammatics. You can just flip through the book, and if you understand it, you don't understand it, it's okay. But it's just there as like you can return to it, and it's not meant for you sit down and struggle with it and also. But really, it is coming from a place of mathematics and trying to satisfy certain axioms. And this is just a number, any number. So if you give me any number, I can write it in this system, essentially. So this is, let's read it. You have 2 5s, 2 2 5s, 2 5 to the 0, so it's 2 in the units place. You have 3 in the ones place. You have 1 2 3 4 5 in the hundreds place, and then you have 9. So 9 5 3 2. This number can be written. The number 9,532 can be written like this or like this. This is in base 10 because these are tens. So you'll notice that this bubble with the 1 on it, mark on it, is really a multiplication. Anyway. So here is a glimpse into like looking at it in an ordinal way, where you start counting, okay, like I'm going to start counting on this ring, or I'm going to start counting on the next one. That's the first, the torus, the first, so I start counting there, or then I go to the next one, or the next one, etc., etc., and that's sort of like going somewhere. And here are some, for the people who wanted the algebraic rules. This is really what's going on here. Like you have a number is really, like you can call it B. It's on, it's really the number of circles on that original base 0. Let's call it base 0. And if it's surrounded by a circle, then that's raising it to the power of 0, which is 1. So anytime you have any expression that is covered by a bubble without anything, it's a 1. If it's covered by a 1, that's b raised to the power of 1. If it's covered by a 2, it's b raised to the power of 2. And really, it's like a notational visual thing. Then you go on to here, which is really 0 to the 1 is 0. 0 to the 1 is 0, 1 to the 0 is 1, 0 to the 0 is 1, 1 to the 1 is 1. Which, again, this is what it looks like here. Here are some rules, which is the multiplication and addition. So, if you have two numbers that are surrounded by a 1 raised to the 1, that means this is again like a convention, but both of them, that means that all of these expressions are the same, basically. So a times b can be written in all of these ways. And a plus b is really you're threading the a and the b with that, right? Now we'll just see a few things here, which is I really wanted to work with a more general idea of like the inverse of a number, which could be the multiplicative inverse, the additive inverse, just any plain old inverse, use all of those notations, but you use it, this is my notation for it, so it's like you have a with a distinction inside and a distinction outside, like a bubble inside and an outside, so it's sort of, that's what I use as a inverse. And so this is the theorem of reflection, where if you take the inverse of the inverse, you get the thing you started with. And really the proof here is you have a distinction inside and a distinction outside, and then you have another distinction inside and a distinction outside. And here's where Spencer-Brown's double cross equals nothing. You can erase the two and you're left with A. So Spencer-Brown's loss of form is implicit in this. And I can go back to that slide later. but I'm just trying to cover this in a little quicker. So here's another rule I introduced, where if a number and its inverse interact, they annihilate each other, so you can erase them. So here, in the context of addition, if A meets its additive inverse, they both disappear and you're left with 0, which is the additive inverse. And here, if A and its multiplicative inverse interact, they both disappear, and you have the bubble with the 1, which is this is a 1. So you're left with, you have this, you're satisfying properties, the group properties of anyway. So here is more ways of writing numbers. This is the fairy sequence. If you've heard the fairy sequence, Lou has talked about the fairy sequence a lot. Really, it's a way of writing all of the rational numbers that we know. We start with a fraction a over c, b over d, and then you write the number in between just by adding the numerators and adding the denominators. And here you start with 0 over 1, 1 over 0. Then you get 1 over 1 because you're adding the numerators, adding the denominators. Then you do the same thing with these two and you get a half, 1/3, 1/4. You can keep using this as a rule to generate all the rational numbers. Same thing, you can do it here, 1 over 1 and 1 over 0. You get 2 over 1, 3 over 1, 4 over 1. You get all the natural numbers, you get all the fractions like inverse of the natural, multiplicative inverse. So this is a very neat visual way of creating all of the rational numbers, and this is what it looks like in my system here, which is really the 0 over 1 and the 1 over 0 are written here. And of course, the next thing I want to go to is continued fractions, because that's going to give me real numbers, and I would like to represent real numbers in the system as well. And so this is what continued fractions look like. And this is what the translation is in our, is A plus B over C plus D over E plus F over G blah blah blah. So you can keep going there, right? So that's your continued fraction form. And again, you know that I would like to circulate the whole ordinal picture onto itself. So this is me trying to do that in a certain sense, but it's not really accurate. It looks like an artistic something. This is one possible solution. Like, okay, this kind of looks like the projective number line in a sense. And this is also, I guess, an attempt for me to create circular matrices, whatever that means, you know. Because I feel like I was trying to go away from this boxedness and go back to circularity. So this is a way of looking at circular matrices. And here is an open question I have for everyone here, which is like, okay, what if we were to do the continued fraction but circle the continued fraction onto itself? What kind of a number is that? You know, is that, because we know that all continued fractions, like the infinite continued fraction, like 1 plus 1 over 1 plus 1 over 1 plus 1, that's the golden ratio, right? And we know that we have different forms, like pi has its own continued fraction, like e has its own continued fraction, like an infinite thing, like a sequence of that. But if we were to algebraize it and circulate it, what is it going to do? I don't know yet, but I mean, this was a question that was in my head. I was like, okay, I would like to draw this picture and offer it as as something to meditate on, if you know. So I guess this is not a continued fraction, but a continuing fraction, let's say, I guess. It just keeps circulating. So yeah, that's basically it. I mean, then there's of course a little bit of other things, and this is what we had seen earlier, which is you start with a distinction, but when you make the distinction, you have an orientation when you make it, because it just doesn't appear like that. We are drawing it, and the act of drawing the distinction gives you the orientation, and that gives you either you do it like that or you do it like that. That gives you really, it's like a circular map of what's going on here. And I'm very fond of drawing these kinds of circular maps, so I'm going to show you one, which I think, if I can find it, yes, right here. It's not a great picture, so I apologize, but really it's this And I'd like to bring your attention to the beginning of Laws of Form, where he says something. I can actually pull that up. Laws. Yes. So we see the theme of this book is that a universe comes into being when a space is severed or taken apart. The skin of a living organism cuts off an outside from an inside. And we've talked about this in the context of cells recently. And what I also would like to share with you is, let's take our skin, right? For a long time I had believed that, okay, it is true that my skin distinguishes who I am, like the inside from the outside. But if we were to look at our orifices, I guess, really, it's an involution of the outside is like inside. You know, like the organs are really pockets of the outside that are inside us. So really, we are genus 1 or 2 or 3 beings. Like that means we have holes. We're not really perfectly distinct things. So there is a kind of I guess a torus-like view of the organism, that we are filled with, you know, voids, that we, like, you know, I think there was a question actually Mark Johnson had about that, and I just wanted to bring that up. So I would like to show you that this picture of like this involution happening, where you start with the circle and then it really starts, you know, eating itself, and this process can continue. And I'm sorry, it's so not great, but if you can just focus on this part right here, you see that the circle becomes a circle within a circle, really. And it's, again, this is one circular map, and that's going to go somewhere. And then this, of course, is going away somewhere else, and somewhere, you know, you can keep using one boundary, but folding it into itself to create boundaries within boundaries within boundaries, and then you can idempose those and just erase those, really. So, you know, it's all coming from one distinction, and you can see it that way. Of course, some interesting things I would like to share about this, and I'll probably close there and open it up to questions, because I'm very curious if this structure or this sort of, really, I would like to ask if this idea of like supercoiling, or this idea of, you know, re-entering the right-hand rule onto itself to create higher genus surfaces, if you do observe this happening in other processes, I would be very curious to hear about them, because I think it's really fun to see. So one such thing is right here, which is in Wheeler's Geometrodynamics. There's a chapter here. I'm just going to show you it's just right here in this chapter, and where he does talk about really a similar thing of like you are kind of let's see where it is. The simplest variety right here is most easily visualized as a standing electromagnetic wave, or a beam of light bent into a closed circular toroid of high energy concentration. It is held in this form by the gravitational attraction of the mass, blah, 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 blah. So I have no idea what this means, but I am very curious to learn and study this aspect of what Wheeler is talking about, and if anyone does know this already, I would love to talk to them soon. Then I do want to talk about something else as well here, which is the 7-color map theorem on toruses, or tori, which came from Haywood's map color theorem paper. And this is really a 7 coloring on the torus, and I feel like there's it's just interesting to think about this, the torus, and you know, having 7 distinctions that you know, you need 7 colors to color a torus, and I think that there's something in this that I would like to connect with the other system to see, and I was trying to think about the octonions as a way of doing that, because you're having 7. And of course, this is a Haywood's map, but as a tessellation of hexagons. I mean, you can tessellate a torus, you just tile it with hexagons, because you have one hexagon is surrounded by 6 hexagons, and so you have 7. You need 7 colors essentially, because you need 1 in the middle and then 6 around it. So I mean, this really, you know, you can wrap this on the torus. So I do, yeah. There's something here that I do try to start doing here with the octonions and this, you know, this diagram that you've already seen, I think. Yeah. But I'm not going to go in there actually, because it might get too technical. I do want to go to the Library of Babel. I saw Andrew like, but I'm gonna point towards a section in this where it is kind of interesting. Of course, there are hexagonal rooms in the Library of Babel, and I think of this system as a way to sort of talk about how to escape the Library of Babel, I guess. So this section is really interesting. It's sort of, I'm gonna remove the because I feel like this is distracting. But I will, yeah, I do want to bring your attention to that sentence right here, where if you don't know the story, of course, like, you know, they're in a library, and basically it's unending, and there's a big mathematical, paradoxical flavor to it. And there's a sentence here where Borges says, the mystics claim that their ecstasy reveals to them a circular chamber containing a great circular book whose spine is continuous and which follows the complete circle of the walls. But their testimony is suspect, their words obscure. This cyclical book is God. And of course, this is like in parentheses, it's just, you know, put in there. So I think it's really funny to read that section, and so, but I was on this quest to really create circular books. So of course I'm very inspired by scrolls, which is part of puppet theater tradition. You have like cranky boxes, you have 2 sticks, and you know, you're really you have a long scroll of paper and you want to scroll something. So I thought that the best way to show the circular number theory work would be in a circular book. I mean, I was like, I wanted it to be circular throughout. Like I wanted this everything, like what Borges was saying. That was something I was thinking about. So I just wanted to show some pictures of some attempts. So I did have, like, you know, these prototypes of, okay, I wanted circular pages, and, you know, like kind of think about, okay, the cylindrical pages, I guess, because, you know, you want. So this was some ideas that were kind of coming up, and, you know, let me just show you some more. Yeah. So you see, like, I was sort of going there, but I still haven't really figured it out. But I do want to show you this physical object right here. This is a sock. And if you've ever rolled up your socks or rolled down your socks, like, really that's what we're doing. That's the kind of motion that I would like to represent in the reading of the book. Like, I would like a spiral bound book that's circular, that you can sort of flip and read, like, in and out, sort of. So this, you know, if you see the motion of this sock, and of course I'm doing the more PG-13 version of it, because you could also use a condom. But I mean, I'm gonna use a sock, but you see, like, this motion of the edge of this torus is really something. And what I would do is I would stitch. I think I'm gonna cut a hole and then stitch it, so then I would have this sort of motion of, like, this continuously unfurling torus sort of shape. So yeah, this is another thing. Sorry?
No, because you could just write the book on a Möbius strip, couldn't you?
Yeah, I think there's there's this idea of, like, just pure. It doesn't even have to be it doesn't even have to have a twist in it. It's really just a circular idea, and this is an idea of, like, the scroll, right? Very. I had made this film, but it's really just a simple idea of, okay, like, I'm gonna scroll it, and, you know, you have mark. It sort of gives this idea of, like, you know, the moving road, and of course I'm just gonna skip to the end.
Only on one side. Did you think if you have a book pages of the book written on both sides, how do you read the inside?
Right, yeah, because I think, so you could see on both sides of the scroll. I mean, you don't, like, this was just an example of what a more simple scroll version I had done earlier. But that's the good question, you know. I think that those questions are very important in terms of finding a way to represent circular number systems or circular representation. Another idea, actually, if you might have heard of this, is called the dream machine. Has anyone heard of the dream machine? It's really like it makes use of a flicker effect to sort of induce a certain rhythm, alpha beta rhythm in your brain. To, you know, it's now, of course you're not going to start sleeping or dreaming, but people like Brian Geisen used it, Genesis P. Orridge. There's a whole documentary about this called Flicker, and really I tried to make a dream machine. It's really a simple thing. You have a turntable, you have a cylinder, and you cut things on the cylinder, and also you have a light bulb that's passed through the cylinder. So you have these slits on a cylinder, and the cylinder is rotating at 33 1/3 RPM or whatever the LPs run on, 45. And you do a little bit of math, and you can control the frame rate basically of how fast or how slow the flickering is happening, because you have a light bulb going through the cylinder and that's rotating. So I tried to make something like that. I mean, of course, something like this, you know, just had a fan and, you know, tried to take a cylinder and basically, I'll just show you like a short video of this, where I tried putting my number system on that. I mean, of course, I wasn't really successful, but it was a start. And I think that essentially is another way I was thinking of having like showing circular systems. Like, okay, you're kind of it's on a moving. It's always moving. It's always circularly moving. And I think that's something I wanted to kind of show. So that's something. Let me see what else. Yes, of course, this is another circular map that, you know, we've sort of, this idea that, okay, it's finally kind of closing in on itself, right? Really, this is another kind of what's happening with this right-hand rule going in on itself, or this sort of magnetic field sort of coming out of the electrical. You know, so that kind of picture is there, and we see pictures like this in laws of form, really, which again no one really has a clear idea what this means, but I feel like maybe there is something going on in these diagrams and what I've been sharing in the just right now. Maybe there's some connection here. So I thought that this, of course, we don't know exactly what was going. I mean, he was using words like tunnels and things like that. So I don't exactly know what the interpretation is, but I'm trying to offer one possible interpretation of, you know, reading those diagrams in laws of form. Of course, we've already seen that. Let's see. Yeah, I think this is a good thing to share, just for our stomachs. Like, I really start talking about laws of form and start looking at a lot of maps around the world, and different cosmological maps, really. So I'm just going to show you a few of these, and then we can close from there. And like, for instance, the shield of Achilles, you know, there is this idea of, like, in the shield of Achilles, the outermost distinction is described as an ocean. And I think this is something that's also, knowing that Homer was supposedly blind as well, there's some connections here of mapping and I don't want to go into it too much, but I'm just going to show you some of these pictures for your benefit. Of course, this is another, you know, more like, if you've not read this book, it's great. It's Scott McCloud, Understanding Comics, where he really is talking about the panel of the comic as, you know, containing what it is we're reading, and he you know, he re-enters his own text and like sees kind of inside the boundary but also outside. Because like the panel acts as a sort of indicator that time or space is being divided. And so yeah, anyway, there's some pictures to just think about, some maps. Really, there's no word for map in Sanskrit. I mean, it's sort of either a picture, a manchitra, like something in your head, or I mean, the closest word like nakshatra, sort of the body. The body and the map are sort of equated together in a certain sense. So, you know, if you, of course, you've seen this before, which is the Natya Shastra. There's some more pictures here. So yeah, I mean, I think that I can end with like OOO, which is really a simple application of this, which is, if you've read Lou Kaufman and Joel Isaacson's work on recursive distinctioning, what I really do is I stick to one-dimensional recursive distinctioning, which is really, if you have something that's distinct within a string of other things that are the same, you have a really simple rule where you substitute these either equals if things are same on either side, or if things are distinct on the right side, you use a right bracket. And so here, this A is replaced by this bracket here. Then the distinct element is you use a O or a 0, and then the next A here is because it's the element on its left, adjacent to the left, is distinct, so you use a bracket, and then all of these are the same. So you see the structures kind of unfolding, and there's something interesting there. And I would highly recommend go to their paper to see just the simple one-dimensional case. And so I start doing that circularly, and so you start seeing that you're basically using this rule, and it will give you. It's almost like a very simple rule that this goes to this, goes to this. And usually we just see the picture, like the top part of this, when we read Lou and Joel's paper. But of course, this can keep pushing out, and you see that at some point it will obviously reach its boundary conditions. And so you get back to this form, which again, this is equal to S3. Which was right here. We just saw it right here. Sorry. Right here, yep. So this one you'll see has returned over here. So you see that you basically start getting, and this is an easy way to look at it, instead of not circular way of looking at it. I just put it in a table. So really what happens is this kind of phenomenon happens when the boundary conditions, like this A is adjacent to this A, you know. So essentially what you're doing is you're doing one-dimensional recursive distinctioning, but this A here is actually also adjacent to that A. So that's essentially what you're doing, and it's like you don't have to write it out circularly if you just say that. So really I start looking at this, and this is just the beginning. And you start, I mean, this is really hopefully an entry into studying modulators and this sort of periodic circular in a circular string, and you have these solutions that kind of pop up. I don't know why, but this is sort of the sequence for which you start having this this sort of modulator kind of periodic structure that comes up from going using circular one-dimensional recursive distinctioning, kind of closing it on itself. So anyway, this is the end of my talk. Thank you very much for this.
10 minutes for questions or
Yeah.
comments. Any from the Zoom?
Yes.
Okay, Nicola.
Okay, so I mean, just a quick. I mean, there were some other questions earlier, but just in that last bit, when you said it closes on itself, you started with an AAA, B, AAA.
Yes.
So what was the B? I mean,
Yeah, so
presumably I mean, was it?
it could start with anything. It could be an CCCCC hashtag CCCCC. So it's basically everything else is homogeneous, and then you have one distinct element there, and you're just studying that case. That's it. It's just you have one distinction in a sea of everything else that's equal to itself. Like you can use the same letter, and then you have one. So that's why using B. AAA is like a more general way, because you're going to substitute that in the next step, because all of those are going to be replaced by equals or parentheses or this zero, which is really coming from Lou and Joel's paper. That's their convention. So you don't need that initial alphabet. Whatever you start with, it gets substituted immediately. So it's really about distinctions. What is adjacent to you? If on your left and right you have the same people, that you are all the same, then you use an equal sign. But if on your left you have something that's distinct from you, then the next step you just substitute that with a bracket, basically. And so you start seeing these like structures emerge, and there's like a tree, there's an ordered tree kind of phenomena that comes up. But,
and the closing on itself is to do with like how many elements you start with before it.
yes, correct. Yep, exactly. So right at the end of the paper, I was giving a list of numbers. Basically, those are the numbers out there. Okay, these are the boundaries that will lead to, this phenomenon of modulators, or you kind of collapse everything. So, yeah. Anyway. Any questions? Any more?
Barbara?
Yeah.
Just a small remark.
Yeah.
It's whether we are really different from the space which is around us. If you take atomic force microscope, you will see that what looks like the border of our skin is not longer there. Yeah.
Mm-hmm.
You go, it becomes very sort of fuzzy. And looking at our current understanding and model of atom, it's mainly the empty space anyway.
Yeah.
So it's a very, I think it's a sheer miracle that we see ourselves and all the material objects as they are.
Mm-hmm, mm-hmm. Yeah, I think on that topic actually I would like to just show something, which is, so if we just look at this, really it's all holes everywhere. I mean, there's this hole here, there are these holes. I mean, they're the tube of but each of these, so it's like you have to imagine a donut circling in a donut way, and so you have holes within, so it's really a lot of that is there. So yeah, I definitely feel that as well. So yeah, thank you.
Yeah, so our real wholeness is our integrity, our spirit, not our body.
Yeah. It feels like it's moving. I mean, there's some. I mean, I can't. I mean, we're really taking snapshot of this picture, and I think the wholeness possibly is like the process of the movement of that maybe.
Which we have to. You see, we have to include the sleep when we sleep, when we dream.
Yeah.
We're still there. Where? In the vacuum space, I guess. And then we wake, and then there's this the wonderful mystery of the material world that we find ourselves in. But to think about our wholeness, we have to include sleeping and waking.
Yeah,
I mean, we spend a third of our time asleep.
Yeah, no, one of the big questions we ask Zen students is, who are you? And unless you come to the point when you really can become nothingness and touch and know that you are nobody, everything falls away, you can't progress.
Mm-hmm.
Yeah. It comes, of course, the answers come in different way, but the fact that you really know there is nothing there, which sometimes really scares people.
Yeah. Yeah, I'm grateful for nothing. I feel like.
Well, no thingness is oneness, isn't it, really?
Yeah.
Yeah, no inside, no outside.
I'm curious if the really bringing it back to this, the right hand rule sort of going back into itself, and if that really, or if anyone else has encountered such a study of that somewhere, because I would love to really go in that direction and sort of think, okay, like if you do have and I tried doing something here, maybe we can show it, like it's really a coiling copper wire on another copper wire, and then coiling that on another copper thing, and I want to, I want to hear what it sounds like, or see what this is going to be like. So, and I probably want to do this again and again and again and again, and sort of, and I realized that actually in audio, in the audio world, like tape heads, cassette tapes, like the head of the cassette tape, the reader is really a toroidal solenoid. It is a loop. It is, and I mean, just solenoids by themselves are used as coil pickups to hear electromagnetic waves. At least we use that when we telephone pickups or guitar pickups or whatever. But if you have tape players, they use the toroidal solenoid. And I'm wondering, okay, maybe there is a way to hear this stuff if we, use that super coiling or whatever right hand rule going onto itself kind of idea, and start paying attention to what they sound like. I think the electromagnetic, what is it exactly? I mean, I don't know, but it's still a question, open question. I haven't tried the experiment yet. But
yeah, I mean, there's so many, isn't it? Because like sounds of the planets and sounds of whales. I mean, obviously when we record them, we're not hearing what, and we are then in a quantum situation. We're an observer, this particular observer.
yeah,
But there's still very interesting ways to go.
yeah.
Coming to near to the end of the session. Anyway, so
Is there anybody?
no,
Yeah.
there's nobody now.
Yeah.
So we've had plenty of discussion during the
Yeah.
presentation anyway. So I suggest that we break for lunch now and go speaker and all these speakers and come back at 2:50.
Great.